you, and you're there, and I'm here, and we're talking about geometry. What a great day it is. Our word of the day is bisect. Our other word of the day is transversal. Our third word of the day is correspond. Our fourth word of the day is vertical angles, but none of them have anything to do with what we're doing in this lesson today, so got them. Hey, we're on page 342, and we're talking about special right triangles, right? Look right up here, special right triangles. They happen when you create certain types of triangles. Specifically, oh, that wasn't the reveal I wanted. This one, an equilateral triangle. And note, you created this diagram in the last topic. Go back and look at video for page 251. That wasn't a reveal either. 251, because we did this. We made a circle around that line segment. We made another circle around the line segment, but from the other direction. And where the circles cross, we put a dot, and we made a three-sided shape. In fact, we call that three-sided shape an equilateral triangle. That's right. Now, what we're going to be doing in our video today is kind of talking about some of the mathematics behind it. What are these special angles and side relationships that we get to use because of what's going on in this figure? Of course, highlight the habits of mind. As mathematicians and learning mathematicians, we are reasoning abstractly and quantitatively. We are constructing viable arguments and critiquing the reasoning of others. This is also directly related to the learning target, the learning goal. Back on page 335, demonstrate the 30, 60, 90 triangle theorem and the 45, 45, 90 triangle theorem using algebraic reasoning. Well, we got to see what the 30, 60, 90 triangle is and what the 45, 45, 90 triangle is. We're going to do the 30, 60, 90 today. When proving the perpendicular bisector theorem and theorems about isosceles triangles, you used auxiliary lines to create right triangles. There are geometric theorems specifically related to right triangles. Let's determine the relationship that exists among the measures of the angles and sides of a 30, 60, 90 triangle. That's the triangle we're looking at today. Consider the equilateral triangle. It's equilateral. A perpendicular bisector AB is constructed which intersects AB at point D. And so we're going to go ahead and acknowledge that AB is intersected by a perpendicular bisector right here. Now I know some things about perpendicular bisectors because I have the card that I've been working on since like page 337 or page 339. And in this, if a point is equidistant from the endpoints of a line segment, then the point lies in the perpendicular bisector of the segment. That's actually worth highlighting the if then statements, because the converse would flip those statements around. And if this is the converse, then the flip around is like the converse of the converse. I don't know, logic. It's an equilateral triangle. It's an equilateral triangle. An equilateral triangle means all three sides are the same length. But why would that be true? How do you know that triangle ABC is an equilateral triangle? How do you know that D is the midpoint of the line segment AB? In fact, are these two circles even congruent to each other? What is the relationship between AB and DB? Things to consider. Let's write something up. Here we go. So first of all, I know that the triangle is created in a certain way, and circle A is the same size as circle B because they have the same radius, right? So I'm gonna pop that in here. I'm gonna move my face picture up over there. Okay. I know that the circles are the same size because both circle A, so I can use a dot with a circle with an A, and I can use a dot with a circle with a B, that those two circles are congruent because they have the same radius. And that radius would be AB. It just kind of flips around depending on which side of the circle you're creating, like which of those letters is your center. Since they have the same radius, they are the same size. So circle A is congruent to circle B. Now, if they're congruent, right, you have circle A and circle B are the same, then any point on circle A will be the same, will be like on the radius, right? So that means that AC is a radius of circle A. And BC is a radius of circle B. So is BC for circle B. Now, all radii of circles are congruent because that's how you make a circle. If you draw a radius here, or here, or here, or here, they're all going to be the same, or here, they're all going to be the same length because that is what a circle does. All of the lines that spoke out from the center, spoke like on a tire, all of those spokes are the same distance. Otherwise, it's not a circle. You have a lumpy, curved line. Same thing for A, but A and B are the same. Circle A, circle B, they are the same. So all of the radii for both circles are the same, which means I get to put a spike on AC, I get to put a spike on BC, I get to put a spike on AB, kind of like on the line. That's a little annoying, but there it is. Okay, good. Now, if all of the lines are the same length in the triangle, so all of these lines are the same distance, what are the angles? How big is angle A? How big is angle B? How big is angle C? They have to be the same size. They have to be the same size because the angles are the same. And if the angles are the same size and they're the same, then it's 180 divided by 3. This is a 60-degree angle. This is a 60-degree angle. This is a 60-degree angle. They're all 60 degrees. So I can pop in a 60 right there, pop in a 60 right there, pop in a 60 right there. Well, I'm almost ready to answer the last question. The last question says, how do you know that you have a 30, 60, 90 triangle? What they're talking about specifically is that angle, triangle CDB, that's really close to something. They should not use those letters. Okay, triangle CDB is 30, 60, 90 because angle B is 60 degrees. It's what we found. But up here, this line cuts angle C in half, and half of 60 is 30. So I'm going to say that. I'm going to say angle BCD is 60 divided by 2, and that would be 30. Now, the last one, on the angle. This angle down here, angle D, it's been created on the perpendicular bisector. That was already stated at the very beginning. CD is a perpendicular bisector, so there's your 90 degrees. Angle BDC is 90 degrees. And there you have it. All three angles, let me get my face over here. All three angles are either a 30 degree, a 60 degree, or a 90 degree when you cut an equilateral triangle in half. Let's talk more about this on page 343. Thanks for watching. Like, comment, and subscribe.